Okay, hello everyone. I'm the host of the channel, KangGO, and here is my very first video in the channel. And today we have a topic of using slide, which is the one principle of the Rocscience model. And this slide is the 6.0 version. And this one slide, I think this one is underdeveloped if we compare to uh, other models. We have the same feature, and this slide model we use it to analyze the slope stabilities, and we can use it in limit equilibrium method and also the finite element method. And here we just go with me and look at what we can find so far in this model. So now I open this slide model and we can see its feature. It's normal. I'm gonna expand some key, and first of all we have to save it. I'm gonna save it in my desktop only. Use practice one. So after save it, we have to take a look for project setting. Project setting, we have the general method, groundwater, transient, statistic, random numbers, design standard, plan, and project summary. Actually, we have to input the project summary first if we conduct the or we analyze the real project. But this one is just only the practice one, so I skip it and take a look for general one. We can see a stress unit, time unit, and permeability unit. I think it all okay for all because our zone is only using in metric. And here we have to careful look for on it. This one is failure direction. We have right to left and left to right. And we can see in this small figure, you can see the direction of failure will be right to the left. So we have to take a look for our model, our geometry, our slope. We have the direction of sliding or of failure from left to right or right to left. So here I have some example. I'm gonna to model this slope geometry. As we can see here we have four different layers of soil, and also I will put the input my parameter here. This one we use it for shear strength analysis in order to get the result of factor of safety of slope stability slope stability. So now we can see this geometry, and we can see the direction that will be fair from the left to the right. So if we keep this right to the left, the slide interpretation will be not done because will not be done because the direction of failure is not the same, and it's not gonna show you the the failure condition of this slope. So we have to change it left to the right. And here we have to take a look for method. As you can see here, there are so many methods to analyze in terms of limit equilibrium method. You can see here, Bishop, simplify, and Spencer, ordinary fairness, GLE. So in this practice, I will use only three reliable, and I think is quite well and widely used in the field. Bishop simplify is unavoidable, and here is GLE. It means the general limit equilibrium, and here is Spencer. So we use only these three, and we will see the result of it, and we can compare it. And this number of slices. Actually, this all this method we slide it in the circular slip surface, and the more the number of interslide, the more accurate our result. So I think I use this default because this default has the number of slide of 25, and I think it's uh, enough. And take a look a bit for groundwater. About groundwater, there are so many choice, but I think for the practice I will not include the groundwater condition, so we skip it, and will be in another video. I can see that here there is something like steady state uh, FEA. This one is for finite element method, and the next video will be about the finite element method in this model. Yeah, so I think enough. Just okay it, and then we have to uh, model our slope uh, as the other example here, geometry here. I think take a look for it a bit. We have to define, we have to model it. So okay now. So let's start. You can see our boundary. Actually here everything is okay now. So here we have to use it for geometry design as external boundary. Actually, we use our cursor to plot it, to sketch it on this model. It's okay to be that, but in case that we have enough coordinate, we have to import it textually by comport the uh, coordinate in this coordinate table. So we'll put the coordinate here. Actually, you can see here I put all the coordinate. Okay, so here our slope geometry. I think it's right to be that. So now we have it, and we have to define the boundary of each layer of soil. If we can see the different type of soil in here. In the example, we see the four different layer within the parameter of uh, the strength of each layer of soil. So we're gonna follow it. Here we have to define the geometry of each layer first. You can see here. Actually, okay. Okay, we have to add material boundary. Actually, here. Okay. Yeah. And here. And here too. Okay, we got it. And then we have to define the material of each layer. So we choose the proper type, and then we define material. You can see there are 20 material here. We just define and add real parameters on each material for only 4. So here I'm gonna put the number of it. It's number 1, and then we take a look for our governs 22 of unit weight. Actually, this all so about the unit weight, stimulus, Poisson ratio, cohesion, angle of shear resist or angle of friction, and angle of the latency. So we look back in our material defined. So we can see we will choose different strength type of strength, and we just use more column because of what? Because we use we see the material given is about this, so we don't have to use all of the given, just use the necessary and required one. So the more column needs only unit weight, uh, strength, normal strength, and the cohesion only. So we're gonna put only here. Yes, 22. I put 100, and oh yeah, angle of friction 44. So here we define the number 2. Take a look a bit. 22.4, 135, 52. I start from 52, 55. Okay, then the number 3, 20, 21.9, 55, 28. Oh my god. Okay, here. And the last one is number 4. It's mean the 4 layers too. 21.6, 70, and 38. Okay, now we define the material already, and then we assign the properties for each layers. Just click on it, click on the material first, and then click on our wanted uh, layers here. Okay, number 2 here, layer number 3. Okay, and first layer. Okay, so we define each material property already. So actually, if we have the groundwater condition, we have to put it by here at water table. But in this practice, I ignore the water condition. So we just only add take a look for surface in order to uh, set the slip surface in the circular slip surface. Actually, we don't have the center of slip surface, so we have to use the auto grid or add grid on it to define the bunch of center of grid in order to make it analyze in each slip layers, and the more we define the grid will be the more accurate in our analysis. So I put here auto grid, and I will put 40 numbers of interval and 40 more for y direction. And here we can see this one is boundaries of our center of the grid of slip surface, circular slip surface. So here will be one of the one among all of center of slip surface, and center of slip surface will cover the slip surface boundary as its radius. And then we after we got all the requirement, we can compute it. Compute what? Compute the uh, model of our slope stability in order to interpret for the result, and then we share it after it, yeah, progress. in here. Okay, and after compute it, we can interpret and get the result of it. So let's see what we can find so far. Okay, we open one, it automatically open one another model, another feature of the Rocscience slide here. It's called slide interpret. Slide interpret here so the safety factor of the our slope stability. So we can see here this all is the bunch of our center of slip surface. So we can see here this one. Why so on this one? 1.986. This one is the critical factors of safety in our slope stability. It means that each one is the minimum value of safety factor in this slip surface. So other what is other safety factor in other direction. We can see here we will choose all surface. We can solve the all surface here. Let's see. Yes, that's all. First, and we can see the legend here. It means that the number of green, the color of green and color of blue here. It means that it will vary from around 1 point. Here you can see this in minimum one around almost to uh, safety factor 6. Yeah, here. So what does it mean? It means that the whole slope geometry here is stable enough, and point us here, and the blue one here, little blue one here is the safest in our slope stability. So it's okay to this slope stability. We don't have to do anything on it like soil nail or geotextile, something like that, because it's stable enough. In case we put the load, distributed load or something on it, it will be reduced in certificate here. So this this practice I didn't put it, but you can practice put it in here. Yeah, loading and add distributed load here. I assume here, so I can put it here, actually here. So I will be compute it again, and let's see the difference after import the loading on the top of the slope. So we can interpret once again. Here we can see the critical safety factor is reduced from 1.986 to 1.911. So we actually can see that the loading will affect to the slip surface and also the safety factor or slope geometry. So here we can show the slice in our slip surface, and then we can also find the each center of slip surface each safety factor here by clicking on query here. Yeah, yeah, this one, yeah, we can see here. This one show the factor safety around about 2.223 radius, and here. So we can see here, we can see another blue one is more than 6, around it will be up to 10 or 14, but the critical one is it means that minimum one is 1.911. So it's not important. I can cancel it and add the two method, because this one is about a bit of simplify. Then we can see the result of Spencer is about 1.879, because the different method will be show the different results. So we take a look for GLE. and here you can see this. So all the result is acceptable even we use the three different method, but the result is quite similar and reliable. So uh, we can assume that our slope here is stable. It's okay to stand alone without any change in the geological or without groundwater condition, without earthquake, and without affecting from climate change, weathering or something. So we can add the material of it here. Also, we can also save it or print it out, the result of it, something like that. So this I want to conclude that this model is really important to analyze the slope stability in various condition. So this one is the simple condition, and hope you all practice in more complicated or more uh, something like additional condition on it. And we hope we can see you again in the next video about this model and also other model in the same feeling, the same field of geotechnical or geology. So I'm gonna stop it from now, and let's see we can meet again in another video or next video. Thank you for watching. Hope you all stay safe, stay healthy in this pandemic. Thank you.